So we are going to continue to work through lecture set number 3 today. I suspect that we will probably finish lecture set number 3 and then we'll move into lecture set number 4. Lecture set 3 has been about developing a process to estimate the parameters of the generalized linear models that we are going to fit. So we left off with an expression for what would be a Newton-Raphson algorithm to estimate the model parameters, so the parameters of the linear component of a generalized linear model. So the expressions that we have written out here are what would be incorporated sort of behind the scenes when you're fitting these algorithms through, say, the GLM function in R. Now, these expressions are not consistent from model to model. So what I mean is these general forms are always going to be utilized, but what gets plugged in for, say, the variance of yi or d mu by d eta, that's going to change with the model you're considering and the link function that you're considering. So we're going to look at an example of one of the formulation of these components momentarily, and we're going to look at it in a fairly easy case. We're going to talk about a Poisson variable with an identity link function, just so that we can get an idea of how this is going to work. But before we get to that part, we're just going to develop a more general expression for updating these model parameters, slightly more digestible, I think. And this will be the formal iterative weighted least squares process that we can utilize to fit the GLMs. Just as a refresher, what we had worked on at the end of last class, so after we finished discussing the Newton-Raphson, was essentially just building the components of a Newton-Raphson for the model parameters. So we know that one of the Newton-Raphson algorithms says your estimate of the MLE on this iteration is equal to your estimate on the previous iteration plus this ratio. And you can have the score function over the information function, which is what we have here, or you could have the score function divided by its derivative. In this situation, we worked out an expression for the score function on slide 15. So that's given here. So this is essentially what we're going to be plugging our current estimate into to try and find to work out the top part of that numerator of the little bump factor. And then what we did is we worked out the form of the information function. So we were able to derive an expression for the diagonal because we already worked out what the variance of the score function is equal to. Okay. And then what we did is work out what the off-diagonal elements are going to look like, which is what we have on slide 18. I just wanted to check something here. E1. Sorry, I'm just trying to recall. We worked on the off-diagonal elements, and then the variance of the score function, we have a solution for, which we would have found in an earlier lecture set. I just want to confirm that. Right, so we worked out, I'm just going to go over this really quickly. So we worked out an expression for the score function. So that's the top part of the little nudge factor in the Newton-Raphson, right? So that's this part here in the numerator of our expression. And then we finished off working out a form for the information function. So in the above, what we computed were the off diagonal elements of the of that information function matrix, or of the information matrix. And the diagonal elements are just the variances of the score functions, which in our case is just the expected value of the score function squared, right? Because the expected value of the score function is equal to 0. So we know the form of that as well. Okay, so we have these two expressions. We're going to look at examples of how we can actually utilize these in practice momentarily. Before we get there, we're going to define the iterative weighted least squares process for the GLM. So this is the starting point for this definition. We needed to understand the structure of the score function and the information function in order to apply this process. And now what we're going to do is simplify this a little bit more so that we can see the general structure for fitting a GLM via this, again, as I keep saying, iterative weighted least squares process, which should sound familiar because we have the least squares process for the normal linear model. And that's going to be a special case of this in the case that we are using a normal linear model. All right. Okay, so we have, therefore, this Newton-Raphson style algorithm is going to be beta equals beta k minus beta on iteration k is equal to beta on iteration k minus 1 plus this little nudge factor. Technically, I shouldn't be dividing these two quantities, the score by the information, because they are matrices in this case, right? So we have this here and this here. So this part would actually be more, this would properly be written as the inverse of the information function multiplied by the score function. So we have this here. Okay, so we can rewrite this equation here as follows. All right, the expression above so we're going to have the information matrix or function for beta on iteration k minus 1 multiplied by beta hat on iteration k is equal to the information function on iteration k minus 1 beta hat iteration k minus 1 plus the score function of beta hat on iteration k minus 1. Okay, and I'm going to call this equation 4 so that I can reference it later. So I of beta can be written as I of beta is equal to X transpose X W X, right? So recall in the process of estimating a normal linear, or the parameters for the normal linear model, we have that hat matrix, which is X transpose X inverse times X transpose Y, is utilized within that process. So this is very similar, right? So now we have X transpose WX, hence the weighted part of the least squares algorithm. Okay. And then we can say here where W is a n by n diagonal matrix with WII is equal to 1 divided by the variance of yi multiplied by d mu I by d theta I squared. Okay. So then we can say the right hand side of 4, which is this part here, is the jth vector of the left hand side with elements. And then we have here the sum from j equals 1 to p multiplied by the sum from I equals 1 to n of xij xik divided by the variance of yi multiplied by d mu I over d theta I squared multiplied by bk, or sorry, beta k hat beta j on iteration k minus 1 plus the sum I equals 1 to n of yi minus mu I xij divided by the variance of yi d theta I d mu I. Okay. Which can be written as X transpose W Z. Okay, so we started from, yeah, thanks. I just saw the comment set to page slide 14. Yes. Okay, so we started with that expression for the Newton-Raphson, and now what we're doing is we're further just breaking down that expression into its components. So we started by moving the information function around. So instead of working with the inverse of the information function, which we probably won't have, we're going to work with the information function directly. So I've multiplied everything by the information function, which is how you arrive at 4. Then we note that the information function, based off the definition we have above, can be written as X transpose WX, where W is a diagonal with the form given here. So it's 1 over the variance of yi multiplied by d mu I over d eta I squared. So you can compare this to what we have on the previous slide to see the relationship between the two of them. And then what we're doing is saying, okay, now we can write the right-hand side of this expression, which is the information function at beta times beta hat plus the score function at beta as follows. So we have these two expressions in terms of, well, we have the information function that we derived above plus the score function that we derived 3 slides back. And then we can say, okay, well, this thing can be written as X transpose W times Z. Okay, and this works. So this can be written as X transpose W times Z, where Z, which is a p-dimensional vector, where Z has elements Zi is equal to the sum from j equals 1 to p I'm just doing with that. J equals 1 to p of xij beta hat j on iteration k minus 1 plus yi minus mu I d beta I over d mu I, where mu I and d beta I over d mu I are evaluated at beta. Okay, so therefore, sorry, any questions? All right, so therefore, we can write 4 as X transpose W X beta hat K is equal to X transpose W Z. Right. And then again, this should look pretty familiar because in the normal linear case, we basically have X transpose X beta equals X transpose Y. Now we have the W adding in the weighted part, hence iterative weighted least squares. And we can use this expression. Iterate to a solution for the beta, right? And we can do that. Well, I'll show you how we can do that momentarily, but basically we can say beta hat on this iteration is going to be equal to the inverse of X transpose XW times X. I should just write this out. We can say, so this is of the same form as what is given for the normal linear models. I'll just call them normal linear models. Okay. So then we can say for GLMs, we start at beta hat 0, compute W and Z, solve for beta hat 1, recompute W and Z, solve for beta hat K, repeat until convergence. All right. So basically, we have this expression now, X transpose WX, X transpose WX beta equals X transpose WZ. We start at an initial value for the beta hat, so some guess or something based off of the data that we're studying. We compute W and Z using the expressions that we have worked out. So here we have Zi, which you can see is a function of the beta, the data, and then the derivative of the linear component, and that's going to change for each GLM. Example to follow. And then we have the expression for WI, which is shown on slide 18. So we would have to recompute this using the derivative of mu I giving eta in this case, which again is going to change from model to model, but may also be, this is also going to be a function of beta. I'm going to show you how that works momentarily as well. So we would have our initial guess, we recompute those two matrices W and Z. We would update for beta K by solving this expression for beta K, which is done just by taking the inverse of X transpose WX and multiplying it by X transpose WZ, get our new estimate of beta, recompute W and Z, and just continue through this process until convergence is reached in some way, which might just mean, as we saw in our example of the Newton-Raphson, at the start of class, just the estimate is basically flatlining and not changing. Okay. Any questions? So this process is called iterative weighted least squares, okay. Or IWLS for short. Okay. Cool. All right, so we have this, what we have now done is established how we can update the parameters of our GLMs. We're going to look at an example of how this would work in a fairly simple case. As you can imagine, this is going to get substantially, well, first of all, there's a substantial amount of matrix calculation and inversion that's involved in the process, right? So right off the start, it's pretty obvious that we're going to run into, well, it's just not going to be feasible to do this in higher dimensional settings by hand. That's the first thing. The second thing is even doing this in lower dimensional cases, like we'll look at a 2x2 example. If you had to run this process for multiple iterations, say like 6 or 7 iterations, in order to do that, you would have to continually reperform these matrix calculations over and over again, which again is really not feasible, nor is it the purpose of the course. For illustrative purposes, we're going to look at an example now where we write out the components of W and Z in terms of the model that we're trying to fit, just so that we can get an idea of how this is going to work. And then we'll look at a single step where we kind of, sorry, one second, guys. So we're going to look through an example just to get an idea of how this would work by hand. But again, this is the process that's happening in R when we fit the model. In lab next week, we'll actually run through the process in R and iterate it ourselves. And then we'll compare it to the actual GLM function to confirm that that is the same solution that's being reached by the GLM function and through our manual process. Okay, so in this example, we are going to fit a Poisson model to this particular data set. So basically what we're doing here is we're assuming that the response variable, which we call yi, follows a Poisson distribution. Okay, and we are going to say that the expected value of the response variable can be linked to xi through the linear component shown below. So we have beta 1 plus beta 2 xi. Basically what we're assuming here is like a simple linear regression model, because we only have one explanatory variable. And we're going to assume that there's an intercept term that can be estimated. But unlike the illustrations that we would have seen of an SLR model in our previous studies, yi is no longer normal. It's instead Poisson. And that's going to have an effect on how we, on the process of iterating, of the process of updating the model parameters, beta 1 and beta 2. Okay, so we're going to assume the expected value of yi is equal to beta 1 plus beta 2 xi. Beta is going to be beta 1, beta 2, and the xi is going to be of the form 1 xi. So the 1 is just put in place there because to account for that intercept term. So the design matrix is going to be a column of 1s and then the xi from the data set of interest. All right, so we're going to set up this problem now. First, so since the yi are following a Poisson distribution, with, do we specify a rate? I don't think so. It really matters. So since the yi are following a Poisson distribution with some parameter alpha, then we can write the expected value of yi is equal to the variance of yi, which I believe is also equal to lambda. But that latter part doesn't matter. So this is a property of the Poisson distribution. So the expected value is equal to the variance. This is something you can prove pretty easily just by applying the definition of the expected value and the variance in the discrete case. You can also check this on like Wiki or something and it'll verify it for you. Okay, so the key part here is that the expected value is equal to the variance. All right. We are fitting a model where the expected value of yi, which is equal to mu I, is equal to, well, I guess in this case, it would be lambda. I'll just change these to mu's so it's consistent. Mu. Okay, so the expected value of mu I is equal to beta 1 plus beta 2 xi. Right. Therefore, we have g of mu I is equal to mu I. Hence, that is, rather than hence, that is, we are using the identity link, right? So you can see that we're simplifying this quite a bit to make the calculations smooth and easy. But so we have a Poisson model. The main takeaway from the fact that it's Poisson random variable is the expected value is equal to the variance. We're going to use this result momentarily. We're fitting a model of the form mu I equals beta 1 plus beta 2 xi. So therefore, what we're saying is that g of mu I is equal to mu I. So we're using an identity link. Okay, so this is also going to be helpful to us momentarily. Okay, so since g of mu I is equal to mu I, d, oh, sorry, and then there's one other thing. Just to make this part clear. So we are saying g of mu I is equal to mu I, and that's the same thing as eta, right? So we let eta represent the link function. Okay, so since we are using the identity link, it follows that d of mu I by d of eta I is going to be equal to 1, because we're basically just saying the derivative of mu I with respect to mu I, which is going to be 1 in this case. Right, so that's the first thing, which makes this pretty clean. For the IWLS process, we have WII is equal to 1 divided by the variance of YI, 1 over the variance of YI, d mu I by d eta I squared. So we have, just want to write this properly, 1 over the variance of YI, d mu I, d eta I squared. So this is going to be equal to 1 over, and then we're going to have 1 over the expected value of yi, which is the mu I, which is beta 1 plus beta 2 xi multiplied by 1 squared. It's equal to 1 over beta 1 plus beta 2. Okay. First result. And again, fairly simplified given the situation. The identity link makes a lot of this a lot easier, right? So if we didn't have the identity link, if we were using a different kind of link function, it would not be necessarily as straightforward. So we have W is equal to this, and the Zi, so I'm just going to snake this from the previous page. And the Zi should simplify to beta 1, beta hat 1, k minus 1, plus beta hat 2, k minus 1, multiplied by xi2 plus yi minus beta hat 1 Okay, well, I guess we can write these. Does it say? Okay, this isn't the clearest explanation, but so we can say minus the mu I. So the mu I we know is equal to the expected value of yi, which is going to be beta 1 plus beta 2 xi. We're going to write this particular part in terms of the estimates rather than in terms of the actual model parameters. So what I mean is we can say like yi minus beta hat y k minus 1 plus beta hat 2 k minus 1 xi2 since we're on the kth iteration in this case, such that this thing simplifies to yi. Okay, and then we can say where beta 1 and beta 2 are replaced by their estimates on iteration k minus 1. Which in terms of the actual model fitting process makes sense because beta 1 and beta 2 are the population values, which are actually unobserved and we're trying to estimate. So within the IWLS, we're not going to be just holding those constant as parameters we don't know, right? So it makes sense that within that process, within Z, on the kth iteration, we're going to replace the estimate of mu with the beta 1k plus beta 2k minus 1 times xi2. All right. Sorry, any questions? Okay, so we have Z, we have W. So then we can say it follows that X transpose W X can be written as the sum from I equals 1 to n of 1 divided by beta 1 hat plus beta 2 hat xi, sum I equals 1 to n xi beta 1 hat plus beta 2 hat xi, sum I equals 1 to n xi beta 1 hat beta 2 hat xi, sum I equals 1 to n xi squared beta 1 plus beta 2 hat xi. Okay. And X transpose W Z can be written as sum I equals 1 to n yi divided by beta 1 hat plus beta 2 hat xi multiplied by the sum xi yi divided by beta 1 hat plus beta 2 hat x. Right. What is this thing? Okay. All right. So now we have the two sides of our iterative weighted least squares equation. So again, the purpose of this illustration was to show basically like how you would go about deriving these to the left-hand side and the right-hand side of the expressions of this IWLS process. And again, there's a few things to take away from this. Like this would be a very simple situation where we have nice expressions for the derivatives that are of interest to us. And we have nice expressions for the mean function as well. So the way that the matrices work out is pretty straightforward. This is also a two-dimensional illustration. So we only have the y and x in our data set. You can imagine that as the dimension increases, the sizes of these matrices is going to increase as well. So the complexity behind these algorithms is, it increases substantially from dimension to dimension. So the last thing I want to do is just kind of walk you through like what would actually happen, just to try and paint this picture as best I can. So the IWLS takes X transpose WX on iteration K minus 1 multiplied by beta hat on iteration K equal to X transpose WZ on iteration K minus 1. Right, so you can see now from the form of X transpose WX and X transpose Z, what I meant before when I was saying these are updating based off the current iteration. So all of the beta hats that we have inside X transpose WX and X transpose Z, those are going to be from the previous iteration. And then basically all we have to do is take the inverse of X transpose WX. All we have to do is take the inverse of this matrix, multiply it by X transpose WZ, and you get a new estimate of beta. And then you reformulate X transpose WX, X transpose Z, take that process again, and you just keep updating until, probably convergence and model parameter is reached. So just the parameters aren't changing much anymore. But the criteria by which you determine convergence can be, that can change depending on the problem. All right, so let's see here. So from above, so we have y is equal to 2, 3, up to 15. Okay, and we have x is equal to 1, -1, 1, -1, 1, 1, right? So again, the X is the design matrix. So we have that leading column of ones to account for the intercept term. And then the second row that I've shown on slide 22, that's just the data that's given in the original table. Okay. All right. Let beta 1 hat beta 1 on iteration 0 equals 7 and beta hat 2 on iteration 0 equal 5. Okay, so then, so given that, basically all we have to do now is plug those values in and then sum across the expressions given in each of the different components of these matrices, right? So what we're going to end up with is something like X transpose WX is equal to 1.821429 negative 0.75 negative 0.75 0.25, and then X transpose WZ is going to be equal to 9.86 9048 0.5833. Okay. Therefore, beta hat on iteration 1 is going to be the inverse of this thing. And that gives 7.45124.937. And then we would just repeat that process again until convergence. All right, any questions? Okay, so assuming there's no questions, again, this lecture set was basically about how GLMs are fitted in the general case. So GLMs are fitted using this IWLS process, the iterative weighted least squares. Pretty similar idea to the weighted least squares process that's used in the MLR case. So in the MLR case, we have that X transpose X inverse equals X transpose Y matrix. Same idea here, except we're weighting the X transposes using the matrix W, where the form of W is going to change depending on the structure of the GLM that you're going to be fitting and the linear component that's associated with it. This IWLS process is essentially a Newton-Raphson algorithm. So that's why we started off the lecture set looking at the Newton-Raphson and the associated properties of said distribution or of the algorithm. And we also looked at it in the lab. So that's going to conclude our example on the iterative processes that are associated, or on the general idea for parameter estimation for GLM. So how we're going to fit these models. Again, for the most part in this course, we're going to be using R to fit the models on assignments, and we're going to learn how to use R to fit GLMs in lab in a few weeks. But it's still good to have an understanding of what the process is behind the scenes. You know, even though for the most part, this is something that's never going to be done by hand, it's still good to have an idea of how how the algorithm is being structured. Okay. All right, so we're going to move on to lecture set 4. So lecture set number 4 is about inference for our generalized linear models. So far we have talked about the formulation of a generalized linear model. So that is through a response variable that is in canonical form from the exponential family, the definition of a linear component, and the definition of a link function. Then we said, all right, how do we actually fit these models in practice? That's what we just concluded with in lecture set number 3, and that's done through this IWLS process. Okay, so we have formulation, we have model fitting, right? The next thing we're going to talk about, and I realize we're skipping a step here a bit, is inference for the GLM. So technically this would be step 4. Diagnostics for GLMs are not as clear cut as they are in the case of the normal linear model. So one thing that kind of gets lost, I think, when you're studying regression analysis, at least in the case of the normal linear model, that process of residual analysis works really well when the errors are normally distributed, right? So comparing your estimated residuals to the quantiles of a normal distribution is a very smart thing to do because you're assuming normality. But once we move past the normality assumption, you can't compare residual estimates to the normal distribution anymore, because that's not going to have any meaning if you're assuming the response variable is binomial or Poisson or some other non-normal distribution. So through talking about inference, we will talk about we'll talk about goodness of fit tests. So measures that you can use to evaluate whether or not the fitted model is useful to you. So that can be done through through the deviance. So some diagnostic elements will be a part of the discussion on inference, but we'll also talk about hypothesis tests for comparing the models, which would be more of a traditional style of inferential process. So there will be some diagnostic components incorporated within this lecture set. There will also be some inferential components, but in general, what we're going to talk about is goodness of fit of the models using hypothesis testing and model comparison using hypothesis testing, hence the inference for GLMs rather than diagnostics for GLMs title. Okay, so we're going to review the definition of statistical inference very briefly. We're going to talk about structures of hypothesis tests for comparing GLMs. And then what we're going to get into is looking at the sampling distribution of our score statistics. So as I had alluded to in my little introduction there, the way that we evaluate and use these models is going to change with each of the response variables changing. So once I switch from a Poisson to a binomial, the work I did to derive the score function, for example, in the binomial case is no longer going to apply. The steps that we go through will, but the results are going to be completely different, right? So we're going to look at different illustrations of how to derive score statistics, which we've talked about, and then the sampling distribution of said statistics as well. Then we're going to discuss the deviance measure. The deviance measure is the primary goodness of fit statistic for GLMs. So our output, for example, always gives you a deviance value, so a measurement, and we're going to talk about what that value means and how to interpret that value and how to use it. And again, it's essentially a goodness of fit statistic that indicates whether or not the proposed model is a good fit to the data compared to what would be considered a maximal model, but I'll come back to that later. All right, and then we'll look at an example of how we can compare two GLMs. When we compare GLMs, there are restrictions. So we can't compare like a Poisson model to a binomial model on the same data set, which makes sense because if you have data where the response variable is a count, you're not going to try and fit a binomial model to that anyways. So the model comparison works when you are looking at subset models within the same family. All right, so there's two main tools when we talk about statistical inference, which are hypothesis tests and confidence intervals. For GLMs, we can use both. I'm sure that you're familiar with the definition of a confidence interval and the definition of a hypothesis test, but very briefly, a confidence interval is two values that's giving you an indication of where the population parameter of interest might be located. A hypothesis test is a tool that we can use to essentially ask a question about the fitted model. And the most general question would be, does this model fit the data well? In our situation, the hypothesis tests are always going to be comparisons. So in the case where you fit one model, there's a default where you compare to what's called the saturated model or the maximal model. And I'll come back to talk about that once we get there. And we can also use hypothesis tests to compare distributions that are making the same assumptions. So that are using the same link function, the same response variable, but one is a subset of the other. Okay, so we can structure hypothesis tests in that way to compare additional terms. Right, so this would be the same as an extra sum of squares F test in the case of the normal linear model. All right, so the general process for fitting or for comparing two GLMs is laid out on slide 4. 6-step hypothesis testing process. I always teach hypothesis tests in 6 steps, so this one is slightly different. Basically, we have a set null and alternative. So the minimal model M0 fits the data well versus the alternative that a larger model, which we call M1, is required. So H0 is going to consider the smaller of the two models. We then compute a goodness of fit statistic for G0 and G1. This can be, for example, the deviance measure, which we'll talk about later. We then calculate an improvement. This can be done by subtracting the values or by dividing them. We're going to talk about the distributional assumptions associated with the deviance. So if we subtract them or if we divide them, we still know the distribution of that particular test statistic, which would represent improvement. And then we can determine if this gives evidence for or against the null simply by comparing it to the values from its sampling distribution, which is the general process of running a hypothesis test. All right. Okay, so when we run any kind of hypothesis testing procedure, whether it would be constructing a confidence interval or building a hypothesis test, you have to know the sampling distribution of the statistic that you are working with. So in the most traditional case of confidence interval construction, we typically work with X bar. We know the sampling distribution of X bar, and our confidence interval margin of error is constructed using the sampling distribution. Similarly, if we're running a hypothesis test about a population mean, our measure of evidence or goodness of fit would be the test statistic. We need to know the sampling distribution of that test statistic in order to conduct inference about the population mean. Okay. So if we're working with normal linear models, we can determine the sampling distributions of the different test statistics that we might be working with directly, right? And in most cases, if it's normal, the confidence interval formulas are going to be normal as well, or student T if we're missing population information, or they're going to be chi or F distributed. Sorry, guys, one sec. I need to go to the. All right. So in the situations where the response variable is not normally distributed, we can use, isentropic results like the central limit theorem, for example, which says that as you collect more observations, the distribution of the sample mean is going to converge to a normal distribution. In these situations, though, the results of these large-scale isentropic properties require various regulatory conditions be met. But fortunately for GLMs, where we are using a response variable that comes from the exponential family, these properties are met. So we can rely on these large-scale results. All right. Okay, so a reminder of a few basic results. For example, if S is the statistic of interest and you standardize S, you get a normal distribution or a standard normal distribution. That's assuming the variance of S is known. If you square a standard normal, you get a chi-square on 1 degree of freedom. Okay, so these are some basic results from Stat 266, I would imagine, just showing the distribution of a standardized random variable and the square of a standardized random variable. Okay. If S is a vector of length P, we have a similar result. So assuming, given the expected value of S and the covariance matrix V for S, we can show that S minus its expected value transpose multiplied by the inverse of V times S minus its expected value is a chi-square on P degree of freedom. And this follows pretty naturally from the first line. We're just talking about the situation where we have P dimensions now. All right. So if Y1 through Yn satisfy the properties of a GLM, we have these results that we derived earlier. Okay, so just a refresher, because we're going to utilize these or some of these momentarily. And we can say that since the expected value of yi is equal to mu I, then the expected value of the score function is equal to 0, and the information function is equal to the expected value of mu j times mu k for jk and 1 to p. Okay, so if we have one parameter, beta, the score statistic has a normal distribution, which then has a chi-square distribution. If we have multivariate parameter beta for beta 1 that contains beta 1 to beta p, then the score function transpose minus or times the inverse of the information function times the score function is a chi-square on p. Okay, so this follows from the previous values given before, essentially. And again, this is true because response variables in the exponential family meet the regulatory conditions that are required for the asymptotic results, like the central limit theorem, which says that as n grows very large, the distribution of the statistic, in that case, the sample mean, is normal. All right, so let's look at an illustration. So we're going to derive the score statistic in the case of a normal distribution and the corresponding distribution of the score statistic. Okay, so we have y1 through yn. Mu is the parameter of interest. Sigma square is unknown. All right, so this means that f of yi is equal to 1 over the square root 2 pi sigma squared multiplied by -1 over 2 sigma squared xi minus mu squared. Okay. And then we've worked through this before. So therefore, given that the density is of this form, the log likelihood of mu given sigma squared yi is equal to 1 over -1 over 2 sigma squared multiplied by the sum from I equals 1 to n of the yi minus n log square root 2 pi sigma squared. Okay. All right. So then we can say, basically the score statistic is going to be the derivative of the log likelihood set equal to 0, right? So therefore, the log likelihood is equal to this expression and S of mu is going to be dl by d mu, which is going to be positive in this case. So positive 1 over sigma squared multiplied by the sum from I equals 1 to little n yi minus mu, which is equal to little n over sigma squared y bar minus mu. Okay. First results. The expected value of S of mu is going to be equal to the expected value of n over sigma squared y bar minus mu And this will be equal to n over sigma squared multiplied by the expected value of y bar minus mu, which is equal to 1 over sigma squared sum equals 1 to n the expected value of yi minus n mu right, which is 1 over sigma squared times n mu minus n mu, which is 0. Right? Okay. And that's of course to be expected because we know that the expected value of a square function is 0. We just haven't seen it formally yet, but it's something that you can show using the exponential property or the properties of the exponential family that we derived earlier. Right. Zero, and then we can say the information function, which is the variance of the score function. Okay. It's going to be the variance of n over sigma squared pi bar minus mu, which is 1 over sigma to the 4 variance n variance of the sum I equals 1 to n by I minus mu. Okay. This is 1 over sigma to the 4 times the sum I equals 1 to n of the variance yi. Right, and the variance of yi is going to be sigma squared. So this becomes 1 over sigma to the 4 times n sigma squared, which is n over sigma squared. Okay. And then I'll just finish. Therefore, S of mu divided by square root of I is equal to y bar n over sigma squared y bar minus mu divided by the square root of n over sigma squared. Okay, and then I'll simplify this next time. Okay, sorry, I went a little bit over. All right, so we'll continue to work through these derivations on Tuesday. So again, what we're doing right now is basically setting up an understanding of how the inferential processes are going to work for the GLMs. We're just starting with some introductory examples so that we can understand and recall the process of deriving the score function and the information function and these sort of things. Okay, so have a good weekend. And if you have any questions, I'll hang around. And otherwise, I will talk to you on Tuesday. Oh, and don't forget that the first assignment can be submitted via CrowdMark by the end of the day tomorrow. And then the second assignment will be posted. And I'll talk a little bit about the first term test next week because that's coming up too. All right. So take care, everybody, and chat with you soon.